two more types of nuclear reaction in addition to radioactivity reactions. Two more types of nuclear reactions are fission and fusion. These both, as does radioactivity, result in transmutation of elements, the conversion of one element to another. Now, we said that radioactivity was a spontaneous process, a natural process, a random process, whereby one nucleus decays into another nucleus. Fission is when one nucleus that is heavy, one heavy nucleus, splits into two or more lighter nuclei. You can see in the example that I have here, and there are way more examples than I have listed here. This is just one, but they always take the same form. You can see that one heavy nucleus splits apart into two lighter nuclei. In this case, uranium-235 splits into krypton-92 and barium-141. All kinds of different possibilities, but they all have the same basic form where one thing becomes two. Now, there's also a neutron over here and some neutrons here and some energy here, and that stuff's really important. It really is. It's critical to these reactions taking place, but that's not how we identify it as a fission reaction. We just look at these bigger elements, uranium, krypton, and barium, and say one big element becomes two lighter elements or two lighter nuclei, and we have these extra things as well, these neutrons and this energy as well. Now, if you look at this, you think like, oh, this is nuclear fission. This is essentially the reaction that was used in the bomb that was dropped in Hiroshima in 1945. It's essentially the reaction that's used in a nuclear power plant. It must generate a lot of energy. Well, if we look at this one particular reaction, 200 mega electron volts that's generated here isn't actually a ton of energy. It's maybe enough energy to move a speck of dust. That's it. It doesn't blow up anything, or it doesn't generate enough power to power anything. So what we need is not one of these taking place. We need lots of them taking place. Well, how do we get them taking place? The reason we have a neutron on the left-hand side here is because we put it there. We fired a neutron at the uranium-235. They fused together and briefly became uranium-236. Now that uranium-236 decayed into krypton, barium, and then some more neutrons in order to balance the mass number and the atomic number. Some energy kicked off there as well. That's one reaction. We kick-started that one reaction by firing the neutron at the uranium-235. But we can't keep doing that an infinite number of times or an exponential number of times. We can't keep firing individual neutrons at the uranium because it just isn't practical. So here's what we do instead. We take advantage of the fact that there are 3 neutrons produced on the right-hand side, or 2 neutrons, or 4 neutrons. Like, different fission reactions are different, right? But in this case, we take advantage of the fact that there's 3 neutrons produced on the right-hand side. And if we build this properly, those 3 neutrons can act as these neutrons fused together with more uranium to split more uranium nuclei. So in other words, we fire 1 neutron at uranium, that produces some energy, but produces 3 neutrons. Those 3 neutrons cause 3 more reactions, which produce 9 more neutrons and more energy. Those 9 neutrons produce 27 neutrons and even more energy, and so on and so on and so on. This grows, if it's built properly, this reaction grows exponentially within a tiny fraction of a second. The bomb that was dropped in Hiroshima that used uranium-235, this entire bomb blew itself apart within a tiny fraction of a second. There was about 50 kilograms of uranium-235 used in this bomb. About 3 to 5 kilograms actually exploded. That's it. The other 45 or 47 kilograms didn't explode. They predicted that. The Americans knew that would happen. It literally blew itself apart before the neutrons that were coming out of the final reactions were able to bind with these uranium-235s. So in a tiny fraction of a second, 3 or 4 kilograms of uranium exploded, and that blew up a city and killed 100,000 people. Okay, imagine what it would have been if it had been all 50 kilograms exploding. That wouldn't be possible because, again, the bomb couldn't stay together that long. Now, you can imagine as well the amount of energy that's generated here. If we can somehow harness this to generate electricity, then it's going to be a pretty clean way of generating electricity, right? No fossil fuels produced, okay? And B, it's going to generate a lot, okay? If we can control it. We just have to make sure that we don't build a bomb as opposed to a power plant. Now, what's a chain reaction? That's what we were just talking about. When the products of one reaction, that being the neutrons here, become the reactants of the next reaction. The products of the first reaction are these three neutrons. These three neutrons become reactants in the next one. This becomes self-sustaining because the products are becoming the reactants. We have to kickstart it, we have to get it going, and then it takes care of itself as long as we have it built and designed properly. Nuclear fission generates a lot of energy. A lot of energy. But it doesn't generate as much as nuclear fusion. Fusion is the opposite. Fission, you remember we had one heavy nucleus splitting apart into two lighter nuclei. With fusion, we have two lighter nuclei fusing together to form one heavy nucleus. Now we still have a neutron and some energy over here and so on. But the big thing here, the big way that we identify that this is fusion versus fission is that two light things become one heavy, right? One heavy becomes two light becomes one heavy. Now, this is kind of tricky to get going because we have to fire a neutron at it and turn it into uranium-236. This is even trickier to get going. Hydrogen, remember we're talking about nuclei here, not atoms, but nuclei. A hydrogen nucleus is positively charged, as is every other nucleus. If you get two hydrogens and you're bringing them close enough together to fuse together, they're going to repel each other a lot. The force of repulsion between those two hydrogen nuclei is given by the equation F is equal to KQ1Q2 over R squared. As R goes down, in other words, as they get closer together, F, the force of repulsion goes up, big time up, exponentially up. We have to overcome that force of repulsion in order to make these hydrogen fuse together. We do that by pumping some energy into it. So we got to kickstart it with some energy to get it going. This is not quite the exact reaction that takes place inside the sun, but it's a fusion reaction as well. Where does the energy come from in the sun to cause hydrogen to fuse together with more hydrogen? The sun's really hot. If we have a tremendous amount of heat, then we can overcome the repulsive force between the hydrogen, fuse them together, produce helium-3, another neutron, and some more energy. More energy than we started with. Now we take some of that energy and we cause more hydrogen to fuse together now. So it becomes self-sustaining as well. The sun is hot, really hot. Some of the heat that's generated by the sun causes more hydrogen to fuse together to generate even more heat. And then some of that causes more hydrogen to fuse together to generate even more heat. So we end up having a chain reaction of sorts, not because the neutrons are causing more reactions, but rather the energy that's generated itself generates or causes more reactions. So fission is when one heavy becomes two light. Fusion is when two light nuclei fuse to form one heavy nucleus. Let's compare these in a couple of different ways. The atomic bomb that was dropped on Hiroshima was essentially this. It was a fission reaction. It was a chain reaction that generated a tremendous amount of energy, enough energy to kill 100,000 people and blow up an entire city. The bomb that was developed by the Americans in 1945 was called the H bomb. The hydrogen, not 1945, sorry, 1952, it was called the H bomb, the hydrogen bomb. It was a fusion bomb. It was this one right here. We think of a fusion bomb as being way more powerful than a fission bomb, right? That's why it took longer to develop it, right? That's why it was 7 years after the end of the Second World War that we had a fusion bomb, an H bomb. But is it more powerful? Yes and no. The bomb itself is definitely more powerful. By the way, fission is used in nuclear power plants. Fusion we can't use in nuclear power plants. We can't control that reaction. Okay? It works in a weapon because you don't want to control the reaction then, right? You want it to just grow and grow and grow. But in a power plant, you want to be able to control it, and we can't control that fusion reaction. Is the fusion bomb more powerful than the fission bomb? Yes. Yes, it is. But if you look at an individual reaction, this one's fusion, this one's fission. If you look at a single reaction of fission is actually more powerful than a single reaction of fusion. If we rank these, fission would be more powerful than fusion. Well, how do we reconcile that? The H bomb was way more powerful than the atomic bomb. So how is it that a fission reaction generates more energy than a fusion reaction? Well, look at the mass. Here we're dealing with 4, like 4 nucleons. So 4 times 1.67 times 10 to the minus 27 kilograms. That would be the mass of the reactants here. Here we're dealing with 236. This single fission reaction generates more energy than a fusion reaction because it has way, 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 way more fuel in a single reaction than a fusion reaction does. If, however, you were to take a kilogram of each, like equal amounts, apples to apples here, you're to take a kilogram of fissionable material and a kilogram of fusion material and let them go, then the fusion would generate way more energy. Per kilogram, fusion generates more, but per single reaction, fission generates more. If I was to introduce a third row here, a chemical reaction, how do you think it would compare? Where do you think it would rank in both of these? Energy per single reaction and also energy per kilogram of reactant. Yeah, it would definitely be a third, a distant third in both cases.
So would fusion have more reaction per kilogram?
Yes. Fusion, if I understand your question correctly, the answer is yes. If the question was, would fusion have more reactions per kilogram? Absolutely. Okay, it would take way more hydrogen nuclei to get a kilogram of fuel than it would uranium-235 nuclei, right? Okay, that's why uranium-235 generates more energy in a single reaction, right? Because you have more of a kilogram in a single fission reaction than you do in a single fusion reaction. But if you get enough of this, you get a kilogram of hydrogen, you get a kilogram of uranium. You don't have as many uraniums, but you still got a kilogram, then the fusion is going to generate way more energy. Both of them, though, more powerful than chemical. Well, that's why they built the atomic bomb, right? That's why they build nuclear power plants, is because, I mean, you can have chemical reactions that can generate energy. Like, that's a conventional bomb, right? It generates energy. But nuclear generates way more energy. Even if it's just fission, it still generates way more energy. Now, let's take a look at the risks here, the byproduct risks. So, in other words, what comes out of it? What are the risks of it? Well, fission clearly produces highly radioactive material. Therefore, those products are, well, for lack of a better term, bad news. Those radioactive particles will cause all kinds of things. We talked about that a bit already when we're talking about the types of radioactivity and transmutation, right? When you have radioactive material, it can cause atoms to become ions, And then those ions can undergo chemical reactions that aren't supposed to take place and do all kinds of crazy things that are not supposed to happen. So the products are highly radioactive, and therefore they will cause lots of damage. Lots of people after Hiroshima died of various diseases, not as a result of the actual explosion, but as a result of the radioactive fallout. Now, a fusion reaction, on the other hand, produces relatively harmless products. It produces way more energy, and the initial destruction would be way more if there was ever a fusion bomb to go off somewhere in a city. But the fallout wouldn't be nearly as significant as it would in a fission bomb. We can't really rank chemical reaction in there, right? Because some chemical reactions produce really good products, and some chemical reactions produce really bad products, right? It all depends upon whatever chemical reaction is taking place.